Hey there! In this video, we're going to look at some more examples factoring trinomials, polynomials that have three terms. And the technique we're going to use is by looking at the coefficients a, b, and c, which are just the numbers that we have in front of the variables. And it is important when we find these coefficients that we note if they are positive or negative, because that will affect our method. So we looked at some examples in a previous video, and we saw that this is going to be easiest if our leading coefficient a is equal to 1. So in this video, we'll focus on some things to try if the coefficient a is not 1. And this symbol right here, that equal sign with a line through it, that means a is not equal to 1. The first thing that we should try is looking for a greatest common factor of each of these terms, a GCF. So that is a number that we could possibly divide all three of these terms by. And looking at the coefficients we have in this example, 5, -25, and -30 are all divisible by 5. So we're going to divide each term in this polynomial by 5 because that is the GCF, greatest common factor, the biggest thing we could divide each of those by. And when we're dividing by a common factor, we'll take that factor we just divided by and put it outside of a set of parentheses. And inside of the parentheses is just what we get when we divide. So if we take 5x squared, but we divide that by 5, well then we're just left with x squared. If we take -25x, divide that by 5, then we're left with -5x. And if we take -30, divide that by 5, then we're left with -6. And now, looking at this new trinomial we have left over inside our parentheses, we can see that these coefficients do give us a leading coefficient a equal to 1. So what's nice about this technique, dividing by the GCF, is we might be able to get back to a situation where our new leading coefficient a is equal to 1. And let's review how we can finish factoring in that case. So after we divided by that greatest common factor, 5, we have three new coefficients where the leading coefficient a is equal to 1. Then we're going to solve this number puzzle and find a pair of numbers that when we multiply them together equals the coefficient c, which in this case is -6, and when we add them together gives us -5. So if we're trying to multiply to get a negative number, that means that we need to have a positive number times a negative number. And the possible factors of 6 that we could multiply to get 6 are 1 times 6 or 2 times 3. So to decide which pair is going to work, now let's look at our adding. We know we need a positive times a negative, and when we add these numbers together, it has to equal -5. So the only way to solve that puzzle with these options is if we multiply -6 times 1, that gives us -6, and -6 plus 1 gives us -5. It's tempting here to try to choose -2 and -3, but that would not work because if we multiply together -2 times -3, that gets us +6, and we're trying to multiply to get -6. So going with the two factors that we've just found, we're going to split that trinomial that we had after factoring out the GCF into a pair of factors, and it's just x plus or minus whatever two numbers we found in that previous step. So that is the complete factorization of this trinomial we started with. First, we divided by a common factor so that we could get that leading coefficient a to equal 1, and then we finished factoring by solving that number puzzle. All right, so let's try out another one. One thing we'll see in this example is that if our leading coefficient is negative at first, all right, let's try out another example. And one of the things that we'll see in this example is that if our leading coefficient is a negative value at first, then we want to divide by a negative greatest common factor so that we can get back to a situation where a is a positive number and hopefully get a to equal positive 1. So looking at these three coefficients, the biggest thing that all of those are able to be divided by is 2, and since this first coefficient has a negative in front of it, we're going to make that greatest common factor a negative 2. If we divide each of those terms by negative 2, what we'll be left with is x squared. So that comes from doing negative 2x squared divided by negative 2. Then we have minus 18x. When we divide a positive coefficient by a negative 2, that gets us to a negative. And when we take negative 90 and divide that by negative 2, that becomes positive 45. So now we're dealing with a smaller trinomial that does have a equal to 1. So to finish factoring this, we're going to solve this number puzzle. We need to find two numbers that when we multiply them together equals positive 45, and when we add them together equals negative 18. So let's list the possible factors of 45. To get 45, we could multiply 1 and 45, 3 and 15, or 9 times 5. And if we're multiplying to get a positive value, we need to do either a positive times a positive or a negative times a negative. But since the number that we're trying to add to get is negative, the only way that that will work is if we do a negative times a negative. And to get negative 18, we could use negative 3 and negative 15. When we multiply those together, we get positive 45, and when we add those, we get negative 18. So to finish factoring this trinomial, we're going to split that up into a pair of factors, x minus 3 times x minus 15. And we still have that negative 2 outside of the parentheses. Once we factor out a greatest common factor, it doesn't affect the rest of our problem, but we still need to include it in those factors because it was part of the original trinomial that we had up here. So here's another example, and something that we'll see in this example is that our greatest common factor can have a variable in it as well as a number. If x is a factor of all three of our terms, then we want to factor out that variable x along with the greatest common factor. So the biggest number that we could divide all three of these coefficients by is 3. And the biggest power of x that we can divide all of these by is x squared. Because x squared is a factor of this last term, and since these other exponents are just higher powers of x, they do really have an x squared inside of them. We can think of x to the power of 4 as x squared times another x squared. And we can think of x to the power of 3 as x times another x squared. So that x squared that we have in our last term is something that we could divide those other two bigger terms by. So that means that our greatest common factor is not just 3, but 3x squared. And if we divide each of these terms by 3x squared, let's see how that affects the trinomial we have remaining. When we divide terms that have coefficients and variables, we're going to divide the numbers. So 3 divided by 3 gives us 1. And we're going to subtract the exponents on this common base x. X to the fourth divided by x squared gives us x squared. Then we have negative 3x to the third divided by 3x squared. First, if we divide these coefficients, negative 3 divided by 3 gives us negative 1, and x to the third divided by x squared gives us x. And when we divide negative 6x squared by 3x squared, negative 6 divided by 3 is negative 2, and x squared divided by x squared is 1. Anything divided by itself is just equal to 1. Now to finish factoring this, we're going to use the coefficients that are left over, and since a is now equal to positive 1, we can use our quick little number puzzle here. We need two numbers that will multiply together to equal negative 2 and add together to equal negative 1. Well, 2 is a prime number. It's the only even prime number, and the only factors are 1 times 2. If we're trying to add to get a negative 1 and multiply to get a negative 2, we need to use a positive number times a negative number. And since the answer we get when we're adding is negative, we need the negative factor to be a bigger number than the positive one. So the final factorization of this trinomial is 3x squared times x minus 2 times x plus 1. So let's do one more example. In this trinomial, we can actually not divide by 6, even though that is the leading coefficient, because these other two coefficients are not divisible by 6. The biggest number that each of these is divisible by is 2. But there's also a variable we could divide by. The biggest variable that all three of these terms have in common is x to the power of 3. Because x to the power of 4 is just x to the power of 3 with another copy of x multiplied into it, and x to the power of 5 is x to the power of 3 with 2 more copies of x multiplied into it. So if we divide everything by 2x to the power of 3, what we'll have left over is, from this first term, dividing those numbers, we get 3, and when we subtract the exponents on the common variable, we get 3x squared. If we divide negative 14 by positive 2, we get negative 7, and x to the fourth divided by x to the third is x squared. And if we divide 4 by 2, we get 2, and x to the third divided by x to the third is 1, so the variables cancel out there. But what we're left with still has a leading coefficient greater than 1. And there's no way we'll be able to divide by something to get this value a to equal 1, because negative 7 and 2 are not divisible by 3. So if a is still not equal to 1, after we've divided by that greatest common factor, we need to use a slightly different method. And I'll go over that method in a different video.